Welcome to the virtual Devnexus and my talk, Memory and Why You Need to Care About It. I understand that this format may not be as exciting as a live venue, but I've been told that the organizers are going to juice this video up somehow to make it a little bit more interesting than just having me present slides and talk to you in this rather flat world that we live in today. My name is Kirk Pepperdine, and I'm a principal engineer at Microsoft in the Java engineering group. And yes, you've heard that correct. Microsoft has a Java engineering group. We've been around for almost 2 years now. I've been performance tuning Java applications for longer than I'd like to admit to. And this reoccurring theme in a lot of my talks comes down to memory. And you might ask, like, why are we talking about memory efficiency? I mean, I thought allocating in Java was quite cheap. And the answer to that is really been the basis of the entire talk. So we'll get into answering, is it really that cheap? Or are there some other things happening here that means that we really need to look after the memory efficiency of our application? And the answer to that question is obviously yes, otherwise we wouldn't get a talk like this. But and we'll deep dive into why. But the primary reason is simply money. Before I wrote this talk, I went out and I looked at a number of the cloud vendors and I said, okay, how much does it cost to get a machine, and what happens if I need to get more memory? And unsurprisingly, I found that if I need to go from one machine to a next machine, a bigger machine, then quite often it was going to cost me twice as much to get into that bigger piece of hardware. And if I just did a little bit of work here and improved the memory efficiency of my application, I could shoehorn that application into smaller hardware and save a lot of money. So with that, let's get into some of the details. How Java uses memory? Not really surprising. We have allocation happening. We're going to use allocators to store data in a data structure within the Java virtual machine. This is typically called a nursery. In general terms, in Java, we're going to call this Eden. We retain the data for some time. If we retain it for long enough, then eventually it will be copied into this other space known as tenured. We access it. Accessing data is generally an exercise in chasing pointers, and you can imagine there's some costs with all of that indirection. And when we're no longer using the data and we've finally dereferenced it, we're going to find that we need to recover that memory. We're going to use a garbage collector to do that, and that's going to give us the sense that we have an infinite amount of memory. There's lots to be said about the other topics, but I'm just going to focus on allocation here. And when we say allocation, I'm really going to focus on the topic of excessive memory churn. The problem with high memory churn is that if you look at that Eden space where it's a fixed size, well, it does elastic down and up a bit, but generally it's going to be capped at a max size. And if I have a high rate of allocation, I'm going to very quickly fill Eden. And when I fill Eden, I'm going to run into this problem where I'm going to have frequent young generational collections. That speeds up the aging process. It creates this condition known as premature promotion, but it's a hidden type, so it's very difficult to detect. Really, you can only see it by looking at the amount of transient data that gets pushed up into tenured space. With all of this excess transient data being prematurely promoted into tenured space, we're going to have more collections of that space and increased copy costs, increased heap fragmentation. And you can just summarize this up as saying, like, I'm going to hyperactivate the garbage collector. And when I hyperactivate the garbage collector, that means I'm going to increase the frequency of collections, and that means I'm going to increase the overall cost of the collection. And this impacts the tail latencies. As a matter of fact, what's going to happen is that your tail latencies are going to become so common that it's eventually going to merge into what your normal response time is for your application. So that's generally not going to be a good thing. Now, the fix for this is to oversize Eden to slow down the GC frequency. But that's the fix that's going to cost you money. And when people have to do this, unfortunately, they look at it and say, well, darn, the garbage collector, blah, 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 bad garbage collector. And to the garbage collector's defense, it's not the garbage collector's fault. It's the memory inefficiency of your application. If you were to take if you're to take a little bit more care in the coding process in terms of making the application more memory efficient, the garbage collector would function quite nicely, and you'd be able to use a much more compact heap, which actually comes with a ton of other performance benefits, as we're going to see as we walk through the problem. One of the things that we're going to talk about extensively is what is behind the cost of a frequent allocation. Now, of course, there's no performance talk without war stories, and here's our set of war stories. You can read them here on the slide, but essentially you can see here that what we're dealing with in all of these cases is some application where people were looking at, like, how do we fix the garbage collector? How do we make the garbage collector more efficient? And the issue is it's not the garbage collector. It was memory. And what's going on here? Well, in the first case, like loads of parsing. In the second and third case, we had APIs that forced excessive amounts of object allocation. And there's all kinds of other things. We see people going off heaps, but then they need to bring the data on heaps. So there's all these marshalling, unmarshalling costs, JSON buffers for microservices, and all of these things that we do for basically manipulating strings are creating a lot of object churn. And by doing something to quiesce that situation, we can actually see some really substantive improvements in performance. So you might ask yourself, like, why? Like, how can we get like a 4x, a 2x? I mean, that's unheard of, right? I mean, everybody's used to, I did really good. I got 5 or 10%. Whereas a colleague came to me the other day and he said, we just did this thing with the heap where we reduced the footprint of the application and we got a 40% improvement. I said, that's fantastic. That's really good work, and quite expected. Whenever you start doing things with memory, you should see these type of integer multiplier improvements in performance. Now, what's going on? So if you look at an allocation in Java, we can say Java heap is a C++ data structure. So an allocation is a manipulation of that data structure. So to allocate, we need to pull pieces of that data structure from memory into the CPU. So that might bring the question, like, well, if the allocation is like so slow, are we being stalled on a memory fetch? And the answer is, well, I don't know, let's take a look. So if we look at a modern CPU, we're typically going to see that they have a ability to retire 4 instructions per clock cycle. On the front end, we can have cycles being stalled because we're unable to feed the back end with instructions, and we get instruction cache misses, and that can get into wasted cycles. And that's a whole talk on its own. On the back end, we can get cycles stalled because of these high latency operations, of which accessing memory is a high latency application. Well, the question is just how high latency is that? Well, we'll take a look at that in a second. But first, let's take a look at this real example. And in this case here, people were mostly happy with this application. You can see that its clocks per instruction is like 1.49, so it's like low. But more importantly, we look at that big red blob over there. That's 54.1% of all of the available clocks are being wasted because this application is memory bound. And you might ask, okay, well, how did it get to be memory bound? Well, if we're randomly jumping around memory trying to unpredictably get data, then there's no way that the optimizers can get in there and try to figure out, okay, what's going on, and try to start feeding the processors with the data that it needs in a very timely manner. And so we spend a lot of time waiting for the processor to get the data that it actually needs. And this can be a long time, because if you look at the structure of our computers today, we can see that we have memory being connected to the CPU indirectly through this thing known as the data bus. And it's really the clock speed on the data bus that's tied to the clock speed on the memory chips that is going to determine how fast we can get data from memory into the CPU. Now, in the design of the systems, the overall computer designers, they look at this problem and they know it's a problem, so they try to balance everything to say, okay, I'm going to do things here. I'm going to use some trickery to try to make sure that that this isn't too big a problem. So I'm trying to get some balance in the system. And one of the tricks we use in the CPU is to add what's known as this two-way associative cache. Now, at issue is it's expensive, so we don't get a lot of it. And not only that, being two-way associative cache means that I need to step into it, and then I need to do a linear walk through the cache in order to find the value that I'm looking for. Consequently, we tend to have a variety of different types of cache. We're going to have a small L1 cache that's very close to the core, and we're going to have a larger L3 cache. In this case, you can see it is a common cache that's backing core 0 and core 1. So that's a common point. So when I modify data, if the other core needs it, it's possible that it could end up in the L3 cache, and then the other core can just pick it up from there, and that saves a round trip to memory. So the relative costs for getting data from any of these caches goes, 4 clocks from the L1 cache, 12 clocks from the L2 cache to the L1 cache, and about 42 clocks from the L3 cache to the L2 cache. Now, getting from main memory into the cache, that's a different calculation. And that really depends upon, again, the RAM chips that you're using. So I picked a common RAM chip to do the rest of this description with. This is like a DDR4 2133. The DDR means it's a double data rate, which means I can transfer data on both the up and down edges of the clock. The 4 means it's 4th generation of the chip, so that pertains to the architecture. We do have other generations. 5 is the newest. It's not very commonly seen because it's new, so it takes a while to seep through the ecosystem. So most of the chips today are going to be of the 4th generation. We also have this 2133 megatransfers per second. So that's the clock speed. That's going to determine how fast we can transfer data. We also have to deal with this other latency issue, which is known as a CAS, which is a column address strobe. So a DDR4 typically has a per request CAS latency factor of 15 clocks. So what it means is that in order for me to get data out of the chip, I need to do some work. I need to strobe the bank of memory that I'm interested in so I can light up the data values that I want. Once I have the data values lit up, then I can read them out, and then I can place them on the bus. So I need time for the signals to stabilize, I need time for the read, I need the time for the transfers and latches and all kinds of low-level stuff that we don't really want to talk about there. But the long and short of it is that takes time, and that's, for these chips, it's about 15 clocks. So if we go into the calculations here, it gets pretty fun. We can see that we take our 2133, we multiply it by 10 to the 9, that's our megatransfer per second. If we have a bus width of 64 bits or 8 bytes, we can now start doing some calculations to figure out that we, in this case, have a transfer rate of 31.78 gigabytes per second. Not bad. Doesn't look too bad, right? So what's the problem? What's the holdup? Well, as you can guess, the issue is the CAS. And so if we start adding that into the equation, we can just go through the calculations here and figure out like how many clocks we're going to have to wait for the CAS to complete. We can see that each column address strobe is going to add 14 nanoseconds of latency. Now, if I assume a 2.4 gigahertz clock, that's going to translate into 33 ticks. And when I add that to the cache miss tick counts, then I'm going to end up with a value of approximately 91 ticks for every single cache miss. Now remember, every time we allocate an object in Java, it's a cache miss, more than likely. Not always, but more than likely. Now, it's not just 91, it's also the time to send the request, to get the data saying I need it, and there's the time to return the data on the bus. So there's no bus time in here. So the bus is shared. So if somebody else is using it, you can't. There's some collision control detection thing working down there, but you get the picture. It's like, it's like a network call. And of course, so this 91 is way on the low side. Now, that's for reads. For writes, the story is a little bit better somewhat. It's better because as soon as I write a value out to memory, it goes into what's known as a store buffer. And after that, the hardware is responsible for proper ordering and to ensure consistency. So that means that if I have a value in core 0 and I write it out and core 1 needs it, then I can be assured that the hardware is going to make sure that the written value is properly seen by core 1. Now, in this case, what we're going to have to do is make sure that that value gets written back all the way to the L3 cache, which means that core 0 might have to stall while that happens, but that should happen very quickly. Getting it into memory, main memory, of course, that's going to be a little bit more latency, but but from the application's point of view, soon I can basically write and forget. So what are the issues with all of this? Well, it turns out there's a cascading set of issues. When we have high allocation rates, we're going to tend to thrash the L1 and L2 and L3 caches, right? Remember, it's like if we have a hot piece of data, we want to try to keep it in the cache for as long as we can. But if we have tons of data just like ripping through the cache, then we're just going to evict the hot data simply because then we need the space. And if you have a hot piece of data and you get a cache miss on every single access, then you can imagine that's going to be an issue. In Java, if you have a lot more garbage collection activity, that's going to be an issue also, because garbage collection is going to rip through memory from left to right. And all that's going to go through the cache, which means you're just going to thrash your caches. And that's going to be a cost. And this is happening at the hardware level. If I'm doing this at the CPU, memory bus level in one application, I have another application running, maybe it's using different cores or whatever, it's being affected by whatever you're doing with this application. And maybe that application runs perfectly well on its own hardware without this interference, but your application is now going to be interfering with all of these other applications running on the machine. Now, you might think, well, okay, things are getting faster, this is all getting better, and the answer is, well, the picture isn't quite as clear as you might think. Now, this is an older chart, but it extrapolates well, and what it shows you is that there's a gap in the improvement of performance of our CPUs and the improvement of the performance of memory. And that's about 8% per year. And you can see this because if you go and look at motherboards that you're buying, if you're assembling your own computer, and you'll go out and buy a motherboard and you can look at it, you'll see the clock speed on the bus. You might notice that hasn't really been changing much over the last number of years. And that's, and that number is really critically tied to the clock speed of the memory chip. Our CPUs, the clocks of them have leveled off as we've gone more multi-core. Yeah, that's absolutely true. but our ability to retire instructions has continued to rise. So that just makes this gap even worse. So how do we trigger this? Well, here's a silly piece of Java code. As one of my colleagues who was reviewing the slides pointed out, you can't even put that number into an int. That's how ridiculous it is. But you can see all we're doing is we're using a spin and create. In all reality, anything that looks like this, the optimizers are going to look at it and go like, poof, I'm going to get rid of it. I'm going to blow it away. It's dead code, right? But, let's forget that. If we're actually executing this, we're going to see, if I look at this timeline where the green is running and the red is stalled, you can see that I do a little bit of work, do a lot of red, a little bit of work, a lot of stall, a little bit of work, a lot of red, so on and so forth. And this is what's known as a revolving door pattern. We see this in a lot of places where you do a little bit of work and then you wait a while. And in the meanwhile, there's a lot of overhead and things that you're inflicting on the environment by, with this particular performance anti-pattern. In this case, the stall doesn't mean I'm not in the CPU and somebody else gets it. The stall is I'm in the CPU still, and I'm just like spinning there like while true, waiting for things to show up. So as far as the CPU profilers are concerned, this thread is 100% busy. And if you're looking at CPU stats in your monitoring, that means your monitoring is completely blind to this problem. It's just simply not going to see it. Now, again, we've been told allocations are cheap, and for the most part they are, but allocations are still a cache miss, and it isn't all that cheap. In fact, the practical maximum allocation rate for an application is 8 gigabytes per second. So we've observed that across different hardware platforms, in different applications, in different environments. It seems to be a consistent now, and it's sort of a function as to how Java applications tend to use memory. In other words, we can get higher, we can get lower, but generally it's in about this range. And even this number really depends upon memory speeds. So as we get faster memory speeds, it used to be like 6 gigs, and then we jumped up in the memory speed, and now we can certainly push 8 gigs per second. But one important takeaway here, this is not tied to the CPU speed. So people are saying, but I'm on the Xeon fast, blah, blah, blah. And the answer is, no, you're probably going to do a little better than this, but really not a lot more, because, look at the memory speeds. So what is an ideal allocation rate? Well, the answer to that is we'd like to see things that are less than 1 gigabyte per second. As you notice, I got this little power curve here, and the range is sort of 1 gigabyte per second above, and the yellow range is like down to about 300 megabytes. Once you get into the 300 megabytes per second range, it's diminishing returns. Even when you get below a gig, you start seeing diminishing returns. In other words, you're going to do a lot of work and you'll get some gains, but you're not going to get the bang for the buck you're going to get if you can get it from X gigabytes per second down to 1 gigabyte per second. The way that I typically find this problem is that when I go into an engagement, I will ask the the people that are engaging me, can you send me your GC logs, whatever you got. If you don't have them, turn on these flags, collect the data for a day or two, send me the logs, and I'll do some analysis. And one of the things I'm going to look at is the allocation rate. And I'm going to say, okay, is this application memory efficient? In this case, you can see the average allocation rate is about 2 point something gigabytes per second. Nominally, and you can see when it's busy, it can range up to like 3.5 gigabytes per second. Don't worry about the noise on the top. This is an approximation, and sometimes you get funny calculations happening here. But if you look at the thick band in the chart, you can see approximately what's going on here. And so this application here, whatever is doing it, is a candidate for memory profilings, and that we're going to find something, and by fixing that, we're likely to get some really interesting boosts in performance. Now, when we do get to the profiling, the memory profiling, and there's plenty of tools out there I could show you how to use. Pick whichever one you want. The one thing that I like to see in the tool is that first, is it going to allow me to look at the allocation rates by frequency, by the number of allocations, not by the size. This really isn't an issue of I allocate things that are too big, although you can do that, but it's generally not. It's going to be how often. So if I have, these 1,000 K or actually 1,000 byte objects that I'm allocating like 100 times, or I'm allocating 100 bytes 1,000 times, I'm more interested in the 100 bytes 1,000 times in that scenario. So I want to sort things so that I see that value. I also would like to see from the profiler an indication as to where the allocation site is in my code. In other words, to get a stack trace from the site of the allocation, so I can look at that information and say, yeah, okay, this is the hot allocation path. And so that's the part of my application that I need to go in and inspect and try to sort out what I can do with it. Now, in some cases, the JVM will help you. There's optimizers in the JVM that will look at the hot allocations, and under certain conditions will say, hey, I know what to do. I know what you're trying to do here. And I can just do a scalar replacement of all of these values. I can inline them into the code and in some way. And instead of allocating them in Java heap, I can just have them effectively immediately here. And that can give you some really nice performance wins. Now, if you're sharing, that's going to cut off this optimization, because if you share data between threads, then all of a sudden we need to do a whole bunch of different things, and these optimizations won't be safe anymore. And there's other conditions where it's likely that it will fail. But if you actually pass this test known as escape analysis, then there's a good chance that that allocation site can be removed from the code, and you can end up with a scalar allocation instead, which would be a lot cheaper. Now, I did mention monitoring at the beginning, or as part of the abstract, and I haven't really talked much about it. But as you can imagine, the things that I'm looking for are going to be initially a nice breakdown of the CPU. And in this case here, if you look at the CPU utilization in the upper right-hand corner, at least as I see it, that we just have this like single green line. And to me, that's really inadequate to understand what's going on at the CPU level. Now, with these types of charts, I don't expect to see cache hit miss rates, although you can probably get an idea of what they are fairly cheaply, so you could put them out there. Even the stall rates in the CPU in terms of the instructions retirement rates, don't really expect to see them. But here I'd like to see like an operating system level breakdown of what's going on to help me understand the issue that I'm dealing with. Here you can just see like I have a green line, and I'm assuming everything above it is idle, but that may not be the case. It may be that it's IO8, which means your thread's in the CPU consuming it, but it's not showing up in this chart. And that means that CPU is not available for other things. There's all kinds of other conditions that you can diagnose by having proper monitoring. But back to the topic at hand, in memory, you can see that there's absolutely no mention of memory churn here, and that's very, very common. As a matter of fact, if you go out and ask people, how much memory does your application burn through, they're going to look at you and say, I don't really know. To that point, you can ask me about a couple of applications I've written, and I'll give you the same answer. So, I don't know, never looked at it, haven't really cared for whatever reason. And that's okay. And if you need more performance, you want to reduce your costs. So this is something that you're going to want to know. And it's probably worthwhile monitoring it, especially when you get into like really, really large deployment environments, because this can in those environments, it just gets trickier to manage performance just because of the scale. And so having a few key performance metrics that are going to give you a lot of information, and certainly allocation rates is one of those things that's going to give you a lot of information, or garbage collection behavior in general. Having that type of information readily available to you, you're going to find is very helpful. I'm not saying that any of this other stuff isn't useful. It's just generally not the stuff that's going to help me track down different issues. For example, I was just with one client where we looked at an issue where they could only use 20% of their CPU. They couldn't use any more because of the conditions that their application put the hardware into. So if they had any diagnostic triggers based on CPU utilization or warnings or anything like that, they just simply weren't going to trigger them. So do try to take care of the monitoring. It's not a matter of broad spectrum. It's a matter of trying to get things that really can give you some deeper insight into what's happening in your system. And with that, I want to thank you for your attention. If you have any questions, please do shout them out. And you can reach me on my Twitter account right here, and there's my email address. So, if you have anything you want to shout out, war stories, or I've had some success looking at this, do let me know. It's always fun to have these conversations. And with that note, thank you very much for attending.